Look around you. The screen you're watching this on, the light illuminating your room, the quiet hum of your refrigerator, the silent power building in your phone on its charger. We are surrounded by an invisible ocean of energy, a force we command with the simple flick of a switch. We call it electricity. But this force isn't just one single thing. It performs an intricate, invisible dance in two very different styles. These styles are known as alternating current, or AC, and direct current, or DC. These two acronyms are everywhere, on power bricks, in instruction manuals, in news articles about green energy and electric cars. But what do they truly mean? They are the lead characters in a story that involves brilliant inventors, a silent war that shaped our modern world, and the fundamental reason your delicate smartphone can draw power from the same wall socket that runs a heavy-duty washing machine. Today, we're going to pull back the curtain on this electrical world. We will journey deep into the nature of AC and DC. We'll explore not just what they are, but why they are, how they work, and how their unique partnership powers every single moment of our lives. So, grab a seat, and let's demystify the electricity you use every day. Let's start with the most essential difference, the very personality of these two currents. If you could see electricity, what would it look like? Let's imagine electricity as the flow of water through a garden hose. The amount of water flowing is the current. First, let's look at direct current, or DC. The visualization for DC is a perfectly straight, flat line. This is because DC is beautifully simple and predictable. It's like a serene, steady river flowing in only one direction. The water starts at one end and flows smoothly and constantly to the other. There are no waves, no interruptions. This is exactly what the electrons in a DC circuit do. They travel directly from the negative terminal to the positive terminal in a single, unwavering, unidirectional path. Think of it as a one-way street for energy. It's constant, stable, and direct. Now, let's turn our attention to alternating current, or AC. The visualization here is completely different. It's a graceful, repeating wave, known as a sine wave. If DC is a calm river, AC is like the tide at the beach. The water rushes in, slows, stops for an instant, and then rushes back out. It's constantly alternating its direction. This wave shows us that journey. As the line moves up from the center, the electric current is flowing forward, reaching its maximum strength at the very peak of the wave. Then, as the line comes back down, the current weakens, stops for an infinitesimal moment at the center line, and then reverses direction. The line goes down, showing the current now flowing backward, reaching its maximum backward strength at the bottom of the wave. This back and forth dance happens with incredible speed. In North America, it happens 60 times every second. In Europe and many other parts of the world, it's 50 times a second. This rate is called frequency, and it's measured in hertz. So when you see 60 hertz on an appliance, it means the electricity is completing 60 full back and forth cycles every single second. It's a blur of motion that, to our eyes, creates a continuous supply of power. So, the fundamental difference is motion. DC is a steady, one-way march. AC is a rhythmic, high-speed, back and forth dance. So, why do we have these two different kinds of flow? It's because they are born from entirely different processes. Let's look at their sources. For direct current, its sources are batteries, solar cells, and fuel cells. Think about a standard battery. Inside, a chemical reaction takes place that effectively creates two sides, one with a surplus of electrons and one with a deficit. When you connect a device, you create a path, and the electrons naturally flow in one direction to balance things out. It's a self-contained, one-way system. This is why everything that runs on batteries, from your TV remote to your electric car, runs on DC power. Solar cells work similarly in principle. When sunlight photons strike the silicon in a solar panel, they knock electrons loose. The panel is designed to guide these freed electrons in a single direction, creating a direct current. Now for alternating current. Its sources are generators, power plants, and wall outlets. AC is the electricity of the industrial-scale grid. At a massive power plant, you'll find enormous generators. The core principle of a generator is simple: spin a magnet inside a coil of wire. As the north pole of the magnet sweeps past the wire, it pushes the electrons in one direction. As it continues to spin, the south pole sweeps past, pulling the electrons in the opposite direction. This continuous rotation, spin, push, spin, pull, is what creates the perfect, wave-like alternating current. That beautiful sine wave isn't an abstract drawing, it's a literal picture of that rotational motion. And because it's far more practical to generate massive amounts of power by spinning things, AC became the standard for power generation. The electricity created is then sent across the country and delivered right to the wall outlets in your home. This next point, voltage change, is the secret behind why our world looks the way it does. It's the reason a historic war was fought over which current would power our future. First, a quick refresher: if current is the amount of water flowing, voltage is the pressure pushing that water. High voltage is like a high-pressure fire hose, low voltage is like a gentle stream from a tap. For AC, changing voltage is easy with devices called transformers. A transformer is a marvel of engineering elegance. It's a passive device with no moving parts, just two coils of wire wrapped around an iron core. By changing the ratio of wire turns between the two coils, a transformer can effortlessly step up low voltage AC to very high voltage, or step down high voltage AC to low voltage. It does this with incredible efficiency, losing very little energy as heat. Now look at DC. Changing its voltage is difficult. It requires complex electronic circuits called converters. Because DC doesn't alternate, it can't use a simple transformer. These converters are more complex, historically were far less efficient, and more prone to failure than the elegant simplicity of a transformer. This single difference, easy voltage change for AC, difficult for DC, set the stage for the next crucial point. This brings us to transmission. This is where AC won the war of the currents. The problem is this: when you send electricity down a long wire, the wire itself resists the flow, and this resistance creates heat. That heat is wasted energy. If you try to send the low-voltage electricity you use at home from a power plant hundreds of miles away, most of it would be lost as heat before it even reached you. The solution: physics gives us a magical loophole. You can transmit the same amount of power by either sending a high current at low voltage or a tiny current at extremely high voltage. And sending a tiny current dramatically reduces the energy loss to heat. This is AC's crowning achievement. Because of the simple transformer. First, power is generated as AC at a plant. Second, a step-up transformer effortlessly boosts it to super high voltages, often over 500,000 volts. Third, this high voltage, low current electricity travels across the country on massive transmission lines with minimal power loss. This is why it's highly efficient over long distances. Fourth, near your home, a series of step-down transformers reduces the voltage to the safe, usable level, like 120 or 230 volts, that comes out of your wall. DC, in the late 19th century, couldn't do this. Without an easy way to change its voltage, it was incredibly inefficient due to power loss over any significant distance. Thomas Edison's DC vision would have required a power plant in every neighborhood. Nikola Tesla's AC system, backed by George Westinghouse, could power entire cities from a single, distant plant. That's why AC won. So, how does this grand system translate to the devices we use every day? Let's look at their common uses. AC is the power of brute force in motion. Common uses include home appliances, motors, and lighting. Big appliances with motors, refrigerators, washing machines, blenders, fans love AC. The natural back-and-forth pulse of alternating current is perfect for creating the rotating magnetic fields that make electric motors spin. But now for DC. Its common uses include electronics, smartphones, and electric vehicles. This is the domain of precision and control. The microchips inside your computer, smartphone, and television are cities of millions of microscopic switches that must be either definitively on or off. They need a steady, stable, one-way supply of power. The fluctuating wave of AC would be chaos for them. It would be like trying to read a book during an earthquake. They need the calm, predictable river of DC. But I plug my laptop into the AC wall outlet, you say? Yes, you do. And that brick on the power cord is the hero of this story. It's a power adapter, and its job is to be a translator. It takes the high voltage AC from the wall, steps it down to a low voltage, and then most importantly, it converts it, or rectifies it, from the chaotic dance of AC into the smooth, steady march of DC that your device's delicate brain can understand. Electric vehicles are a perfect modern example of this partnership. They store energy in massive DC batteries, but they charge from the AC power grid. The charger, whether it's built into the car or the wall unit, is a sophisticated converter, bridging the two worlds. So, in the end, we see it's not a story of AC versus DC. It's the story of a perfect symbiosis. AC is the long-haul trucker of the electrical world. It's the robust, efficient system for generating power and transporting it across vast landscapes, bringing boundless energy to our cities and towns. DC is the local specialist. It's the stable, precise energy stored in our batteries and required by the digital brains of our electronic devices. We've engineered a brilliant system where we use AC for what it does best, long-distance travel, and then seamlessly convert it to DC right where we need it, for what it does best, powering our modern technology. So the next time you flip a switch, or your phone screen lights up, take a moment. Appreciate the invisible dance, the powerful, alternating journey across countries, and the final, direct delivery of energy that makes it all possible. It's the silent, unsung partnership that truly powers the world.